I hope you guys are still doing well and you are enjoying our revision course so far. So now we are actually on lesson 5. And this lesson is titled Elastic and Inelastic Collusions. So our learning outcomes for this lesson is that at least by the end of this lesson, you should be able to distinguish, to differentiate, to tell the difference between elastic and inelastic collusions by calculations. You will see how we do that later in the lesson. So remember, in the last lesson, we spoke about collusions, where perhaps we had two objects that were rolling towards each other and they collide, or it can be an explosion, it can be a gun fired, it can be a number of things. And we spoke about the fact that in an explosion or in a collision, momentum is always conserved. This means that the total momentum before collision of the individual objects is equal to the total momentum after collision. So here now we further that discussion and say that momentum is always conserved for in both elastic and inelastic collisions. So that is something important that you need to know. However, kinetic energy is only conserved for elastic collisions, but not for inelastic collisions. So that is how we're going to differentiate basically between elastic and non or inelastic collisions. So initially, objects in a collisions, they have a kinetic energy because they are moving. And if you remember kinetic energy, the formula for kinetic energy will be K, the symbol for it K, which is measured in joules. And then it's a half mv squared. So this is the mass of the object in question, and it's measured in kilograms. This is the velocity of the object in question. We know that is measured in meters per second, and it is squared. So this this objects initially have kinetic energy because they are moving, because they have a velocity, and then during that collision, in some collisions, that energy is transformed. We talk about the process of energy transformation. So remember, when two objects collide, they make a bit of a sound, and meaning that kinetic energy is transferred, it's transformed from one form into from kinetic energy into maybe sound energy. Hence, that's why in an elastic collision, kinetic energy is not conserved. This means that the total kinetic energy before collision and is not equals to the total kinetic energy after collision. But you're going to do a calculation, and all of this will will sort of make sense. Okay, so now let us differentiate between these two types of collusions by giving out standard definitions. So the definition for elastic collusion is that it is a collusion whereby the total momentum and the total kinetic energy, are both conserved. So the total momentum before collusion and the total kinetic energy before collusion, as well as after, are the same. They remain constant. In an elastic collision, however, the total momentum, yes, is conserved, but the total kinetic energy is not conserved. So the total momentum before and after collision will be the same. However, the total kinetic energy before and after collision will not be the same. The kinetic energy is transformed from or into other forms of energy. We have already spoken about it. It can be from kinetic energy to sound energy when that collision happened. And you sometimes know when maybe two cars collide with each other, there'll be a sort of deformation or whatever you want to call it. So now let us now put this into a bit of mathematical terms. So remember, in the previous lesson, we defined this. We said the total momentum before and after collision is the same. So if we had two objects that were about to collide with each other, and we add their momentum before they collide, we would find that that momentum is equals to their momentum after they collide. So in both elastic and inelastic collision, this equation stands. the total momentum before and after collision would be the same. And then now we talk about kinetic energy, and we said that the formula for kinetic energy as we know it is a half mv, what you call this, mv squared. So now we have still the same case. We have maybe two objects that are about to collide with each other. This is m1, we call this m2. This one is moving at a velocity of v1 and this one is moving at a velocity of v2, and they collide. And so before collision, this will be the kinetic energy of the first object or the first ball, the second one. So this I just means before collision and F means after collision. So if that collision is elastic, this equation will stand. Ki, the total kinetic energy before, will be equal to the total kinetic energy after the collision. However, if it is an inelastic collision, this equation will not stand. So you'd find that the total kinetic energy before and after collision will not be equal. Then we will be able to then tell that this collision is actually in fact inelastic. But now let us now do a calculation where we see all of this in practice. Okay, so we have ourselves a very nice question over here. And the question says, two billiard balls, each with a mass of 150 grams, collide head on. So I don't know where my other marker is, doesn't matter. Collide head on. So imagine these were balls and they are traveling towards each other and they are about to collide. So ball 1 was traveling at a velocity of 2 meters per second, and ball 2 was traveling at a velocity of 1.5 meters per second. After collision, ball 1 travels away from ball 2 at a velocity of 1.5 meters per second. So another thing to note is that it is an elastic collision. So now the first question is that we should calculate the velocity of ball 2 after they collide. And then the second question is that we should actually prove now that this is in fact an elastic collision, and the question requires us to show calculations. So let's just get down to it. So this is the situation that was described to us. We had two balls, they were traveling head on, they are about to collide. So this is before collision, this is after collision. After collision, this ball travels in one direction and the other one travels in the opposite direction. So as we always do, let's say right is positive and then left is negative. And then they said the mass of M1 is 150 grams. But remember, we have to convert this. This means that we have to, if we want to convert from grams to kilograms, we have to divide by 1,000. 150 divided by 1,000 is going to give us 0. Let me write it at the bottom. Is actually going to give us 0.15 kg. You can confirm this on your calculator. And they said the velocity of this, so we decided that it's actually moving to the right. So its velocity, we call that v1I. So this is its initial velocity before collision, is 2 meters per second. So now let us do the same thing. M2, they have the same mass. So M2 also, the mass is 0.15 kg. They said that it was traveling at a velocity of, so we call this v2I. So this is the velocity before collision, and it was traveling. See, it's traveling in the opposite direction to this ball, and we said that direction is to the left and it's negative. So it's going to be negative 1.5 meters per second. Okay, let me write this in a nice way. So V2I is negative 1.5 meters per second. Okay, cool. Then we can do the same thing on the other side. M1 is still 0.15 kg. V1F, so this is the final velocity of this. After they collided, it's now moving in this direction. They say it's 1.5 meters per second, but because it's moving to the left, it must be negative. And then here, M2, it's the same as so-called 0.15 kg. And then V2F, we don't know. That is what we are looking for, if I'm not mistaken. Yes, that is the velocity we're looking for. And now from here, it's just pretty straightforward. We use that formula of ours that momentum, the total momentum before and after collision is the same. So if you use that formula, the total momentum before collision and after is the same, you're already familiar with this. And we simply just substitute everything as it is. Take note that this was going to be negative because this ball was moving to the left, and we said the left is negative. And then after collision, this ball is the first ball is now moving to the left, and that one is moving to the right. So somehow we expect this answer to be positive. And you should be able to actually, this is simple maths, you should be able to calculate this. And at the end, the answer that you're supposed to find, this should just be 0.3 plus negative 0.225, which is equals to negative 0.225 plus 0.15 V2F, because this is what we're looking for. If you take this to the other side, it becomes positive, meaning these two will actually cancel each other. So on this side, we'll have 0.3, and on this side 0.3, on this other side we'll have 0.15 V2F, and then to get rid of 0.15, you simply divide both sides by 0.15, 0.15. This is maths. You should be able to do this on your own. If you're struggling with it, please do let me know so that I can guide you through it. And you'd actually find that value to be 2 meters per second. It's positive, meaning it is to the right. So we have found the velocity of the ball, the second ball after they collided, and it is 2. So V2F is 2 meters per second. So make sure you're able to get the same answer. If you're struggling with anything here, especially with the maths, then you should just let me know on WhatsApp. So now we're moving on to the second question. Remember, the second question wanted us to prove that this is in fact an elastic collusion. The statement said it was, but now we have to prove by showing calculations. So we know that in an elastic collusion, the total momentum is conserved. So definitely momentum is always conserved in either elastic or inelastic collusion. But now in elastic collusion, the total kinetic energy is always conserved. And I have already introduced you to this formula where the total kinetic energy before and after collusion is the same. So you are already familiar with it. So it's just a matter of calculating the total momentum, the total kinetic energy before collusion and after. And if those two values are the same, then we would definitely know that kinetic energy is conserved, and that this is in fact an elastic collusion. So essentially this formula comes to this. We have everything. If you look, we have the mass, m1, m2, the initial velocity for both balls and the final velocity for both balls. So it's just a matter of substituting everything correctly and also doing the calculation correctly on your calculator. So if you substitute everything correctly, you're going to come to something like this. This is going to be negative and this is going to be negative. Let me see. Yes. And then if you calculate this side, so just this is one thing. So it's a half 0.15 multiplied by 1.5 all squared plus a half 0.15 multiplied by 2 squared. I just didn't have enough space. And then you'd find, if you do it correctly on a calculator, you'd find this is 0.469. Wait. 0.469, and we know kinetic energy is measured in joules, as I've mentioned before. Also on this side, you'd find that Kf is also equals to 0.469. So then you can conclude and say that the total kinetic energy, how do you write total? The total kinetic energy before and after collusion, before and after collusion is the same. So this means that kinetic energy is conserved. This means, therefore, this is an elastic collusion. Therefore, this is an elastic collusion. And yeah, I'm not sure if I've left anything except for my terrible handwriting and maybe some spelling mistakes. Just always make sure you check them and make sure it's the correct spelling, because I write very fast. So this will now actually just kind of conclude our series on momentum. conservation of momentum, as well as elastic and inelastic collusions. In the next lesson, we're actually now going to be getting into what is it, vertical projectile motion. So yeah, I hope you've enjoyed this series, and yeah, we'll meet again on the next lesson. I'm trying to think if I've left anything that I wanted to discuss, but yeah, thank you very much for watching.